Hi guys, I'm Antonio Sorrentino from Level Acoustics and Vibration here in Eindhoven, in the Netherlands, and I'm working with machinery noise. Ciao!
Hi, Antonio here. In our daily routine at home, we are surrounded by a lot of equipment such as washing machines, pumps, boilers, speakers. These things while working vibrate. These are what we call structure-borne sources. And about this, if you don't know what is a source and what structure-borne means, I recommend you to have a look to our previous video, where Matt introduces the concept of structure-borne noise and explain why we hear vibration. The noise we hear depends on several aspects: the equipment, the structures, and the way they are connected. Today I want to show you a basic example of how to manage vibrations and sound insulations. So let's move to our lab. Here we are at the Sound Transmission Lab of Level Acoustics and Vibration in Eindhoven, the Netherlands. Sound transmission labs allow us to understand how sound and vibration is transmitted from one room to another. Next to me, I have a small electric motor attached to a concrete block. These two will represent a noisy machine we will use for our sound insulation example. Our machine is connected to the floor via spikes. This form of coupling fully transmits the mechanical vibrations from the machine to the floor. The sound we hear coming from the motor can be described as broadband noise. This means that the motor is producing sounds at a wide frequency range. The origin of this airborne noise is the motor's fan. Inside the motor, there is also an electrical engine with a rotating shaft, which causes this machine to vibrate and transmit vibrations to the floor. Underneath this room, there is another room. Let's go to see what's happening there. We are now in the room below, and as you can hear, the sounds of the upstairs machine is quiet but still audible. This structure-borne noise is caused by transmission of the mechanical vibrations of the motor through the floor into the receiving room. Our motor, which is driven by 50 Hz power grid, is producing vibrations which are multiple of this fundamental frequency. And most of the energy in this noise is contained in the low frequency range. If this was our office, how do we save our ears and our mental health? In most scenarios, our motor will be in a machine room with proper sound insulation, which will reduce the airborne noise from the fan. But how do we reduce the noise in the receiving room? Structure-borne transmission is a complex problem, and each case might require a specific solution. In our case, the solution is simple. We can introduce some resilient material between the motor and the block. The dampening material will act as a spring and dissipate most of the vibrational energy coming from the motor. So, which kind of dampening material should we choose? If we think of the motor and the concrete block as a single mass and the dampers as a single spring, we can model this entire structure as a mass spring system, whose fundamental frequency can be determined by the following simple equation. To achieve good vibration insulation, we must tune the fundamental frequency of our mass spring system to be lower than the frequency of the source activity. In our case, this is the frequency of the engine, which corresponds to 50 Hz. So, assuming the mass of our machine is constant and we know the frequency of the source activity, the stiffness of our dampening material is the quantity we need to set in order to tune the system. Here I have some rubber pads which I have chosen for their stiffness in order to effectively dampen the vibrations from the motor. Let's install them between the motor and the floor, and let's hear the effect.
It sounds quite different. Let's go downstairs to hear how it sounds.
As you can hear, the structure board noise is now almost not perceivable, even though the motor is still on. This means that we have chosen properly our dampers and therefore successfully decoupled the motor from the floor. In my research, I'm dealing with noise due to machinery coupled to lightweight structures. And in such framework, I'm working on two aspects. How to develop a source characterization method suitable for in-situ applications, and how to design the sound insulation for systems like this. In simple cases, like the one we saw in this video, where the source and the structure are quite different, the insulation design and the choice of the modification can be extremely simple. The only things we need to know is the mass of the machine and the frequency content of its activity. In order to safely tune the system, the dynamic stability of the source should be ensured as well. I hope you enjoyed the video, and if you are interested in learning more about acoustics, check out the other videos of Acoutect's channel. Ciao!